So there's this very interesting thing called maximum extendability. Okay, what does that mean? That's, at least to my knowledge, a framework of logic that we're using to figure out what's going on.
There's a feature that a space-time can have. It's a feature called maximal extendability. And roughly speaking, it's this feature that a space-time is as large as it can be. Another way to think about it is that it has no arbitrary boundaries. The only boundaries it's allowed to have are non-arbitrary boundaries.
Okay. Basically, the claim is if you have a minimum of something, the logical extension of that would be, what would the inverse of that be? Well, the inverse of that would be a maximum. Okay. So, to my knowledge, again, I'm not a professionally trained physicist. I don't have a PhD in physics. I'm a dude on the internet that's very interested, like a lot of y'all and everything, and had to have a lot of questions, and somehow became a monk at the Physics Monastery. Okay. Ultimately, a lot of folks, one of the things that you have kind of like with quantum gravity and stuff like that, it's like, all right, we can get down to like the Planck length, and then we don't know what to do after that. Now, that seems to be inferring that we can continue to go down indefinitely. Like, there is no minimum. We can just keep on going, blah, 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 blah. Even though when we do a calculation, we get, well, I just erased the Planck length. There does seem to be a minimum of length. Okay. To our known physics. Now, might there be stuff below that? Perhaps. But the thing is, if you have to keep on going down smaller and smaller and smaller, if we were to follow maximum extendability, if things can get infinitely small, well, the inverse of that must mean that things get infinitely big. So if universe, whatever that is, goes on forever, that's pretty hard to conceptualize. And there seem to be a number of folks that believe that. It believes, okay, we're going to continue outward forever. All right. So I'm going to claim that what if we just took like the physics that we know for the most part, if we have a minimum of length, what would happen if we extended it to its maximum? Okay. So what would that mean? So let's just do the little thing here. We'll show the little bit of magic. All right, as we go back to our friend Wolfram Alpha. Okay. So we've got this thingy that's called the Planck length. You literally just type the word, you hit enter, and then, oh God, the lag is real. The lag is real. Must be ChatGPT and all those LLMs, which seem to be one of the big customers nowadays. Oh my God. This is atrocious. I might have to go back and add some of these things, and let's reload this. Hold on. Let me give myself a new window. Ooh. That's okay. Here we go. Oh yeah, it's definitely lagging on. There we go. All right, back after these messages. We'll be right back. Ooh, some tea sounds pretty good. I might make myself a hot chocolate. All right, we got the Planck length here. What is this? Stuff find is this. It's the square root of the Newtonian gravitational constant, h bar, the minimum unit of action, divide by speed of light to the third power. Okay, it gives you this. What is this? 1.6 times 10 to the minus 35 meters. Ridiculously small. So like an atom is like, I don't know, 10 to the minus 10-ish meters or so. So it's like 25 magnitudes or decimal places difference between the size of an atom. Frickin' small. So hypothetically, how would we extend this? Well, you do that 1 over thing. Okay. Gives you this, but we're in the wrong units. All right. You want to see a little trick? Watch this. Since we've gone over our coherent system of units, the Planck length is expressed in meters. So what happens if we divide it into meters? Well, we've got a dimension of length divided by another dimension of length. It gives us a dimensionless number. But we don't want a dimensionless number. We want a dimension-full number. All right, what do we got to do? Well, since this is 1, we square it. Since we know 1 squared is 1. The 1 shall remain, but there's an additional dimension there because we've gone from basically a length to a square area. Okay. But since we're dividing it by a length, we're going to get our same dimensionless number out within the dimension that we're looking for. All right. What is this? 6.1 times 10 to the 34 meters. An absolutely ginormous number. How ginormous is it? Well, it's right about 100 million times larger than the diameter of the observable universe.